All right, so we are moving on to our next section, which is calorimetry. Okay, so calorimetry is the measurement of heat transfer. So again, the measurement of heat transfer. During this section, there's a few things that you need to remember. Okay, the first is from video 1, that heat is going to transfer from high to low, or we'll say from hot to cold. So when we're measuring heat transfer, you need to keep in mind that heat is always transferring from hot to cold. In order to measure this, so in order to measure and use calorimetry, we are going to use a calorimeter. So we have over here a calorimeter. So this is our lovely example of our calorimeter. We'll see that we have a dual layer of styrofoam cups. Why styrofoam cups? Because styrofoam are great insulators. So think of if you ever go get coffee, most of the time, like Dunkin' Donuts I know does, they'll give you styrofoam cups. Okay, and that again is because it's a great insulator, meaning it doesn't allow a large amount of transfer of energy. So it kind of absorbs that energy. All right, well, keep talking about energy being absorbed and staying in, or sorry, the heat not being transferred. Well, we want to put a lid on our system. So we're going to put, so like a cork, for example, it's a good insulator. So we're going to put a lid so the heat cannot escape into the surroundings. So our system is our calorimeter. So we want to keep all of our heat contained in here. We're going to put a hole then, so we can take our thermometer and place it in our solution of water. Sometimes we'll put a stir in. Sometimes you don't need a stir. So if you don't use a stir, then you only need one hole. If you want to put a second hole in, then you'll put a stir there. Okay, so this is our calorimeter. It allows us to calculate how much energy is transferred from one substance to another. Okay, and our reaction mixture, so we're going to use water. So we're going to put water, and that's going to be how we're going to calculate heat transfer. And then you usually put another substance in there, which is what you're trying to find out about. So, for example, a metal. We're going to put the metal in a cup of water and see how is this energy being transferred. So in order to do this, we need to remember our energy equation, because again, we're all talking about, this whole thing is talking about heat transfer, which we know that heat is a form of energy. So we're going to use our Q equals MCAT equation for doing calorimetry. Okay, because Q, remember, is our heat, and heat is a form of energy. So we're going to see, well, how is our energy being transferred? And again, remember, hot, always hot to cold, never cold to hot. So we're just going to go through. So remember, Q is our energy. We're going to measure that in joules. Our M is our mass. That's in grams. Our C is specific heat capacity. That's going to be in joules over grams times degrees Celsius. And then delta T is our change in temperature, which, remember, is final minus initial. And depending on our unit here, well, since specific heat is degrees Celsius, we're going to work that our delta T is going to be specific heat Celsius. Or delta T is going to also be degrees Celsius. So we're going to go through and we're going to do an example, okay, which is going to take quite some time because I'm going to show you how to actually set up a calorimeter so that when you go into lab, you know exactly what you're doing. So a very simple, basic, common question that a lab will ask is, what is the identity of this unknown metal? So of an unknown metal. So I'm going to give you this block of metal or piece of metal, metal wire, whatever it is, and I'm going to ask you to figure out what the metal is. So how are we going to do this? So we want to kind of look at our equation. So we have Q equals MCAT. So one of these will allow us to figure out our specific heat capacity. Which one is it? Well, we can look at or figure out what element it is, but we can look at our specific heat capacity. So if you remember, our specific heat capacity, we have all those different variables. So remember, water 4.184. So once we figure out the specific heat capacity of this metal, we can look at a chart and figure out, well, what metal is closest to what we obtained. So our first step in doing this is, well, we want to figure out how much of our metal we have here. So, well, we want to figure out how much our heat can be absorbed here. So we're just going to set up a beaker because we have to get heat into our metal. So I'm going to set up a beaker. I'm going to put it on a hot plate or a Bunsen burner, and I'm going to heat it up so I can get some heat into my beaker. So this is a beaker of water, so just normal water. All right, and I'm going to cook it until we get to 93.5 degrees Celsius. And then I say, okay, this is a pretty good temperature. I'm going to keep my water at this. And then I'm going to take and I'm going to place my metal into this beaker. So I'm going to take my metal, change the color of it so we kind of get a different vibe. All right, I'm going to take my metal and I'm going to place my metal in this beaker of water so that we can get some heat into our metal or into what we're trying to find out about, because we need to figure out the specific heat capacity of this. So we need to figure out, well, how much heat can this hold? So we're going to get it to be that 93. So we're going to put it in there for a few minutes. Okay, once we let it sit in there for like a couple minutes, it's going to absorb all that heat. So it is also going to be 93.5 degrees Celsius, just like the water that it's sitting in. Okay, because it's going to absorb all that heat from the water. All right, so, but now we need to figure out, well, how much energy can this transfer? So we can figure out, again, our specific heat capacity. So I'm going to use a calorimeter. So if you look at that last page, we're going to take our calorimeter, which is a dual layered styrofoam cup again because it's a good insulator. Put a lid on it. I'm going to take the mass because I don't want the mass of the calorimeter. We only want the mass of the substances. So I'm going to take the mass, then I'm going to add the water, and I'm going to subtract the mass from the calorimeter. So I'm going to find out, all right, I have 118 grams. So put it on my scale. All right, my scale is going to read 118 grams. So our water, we're going to say, weighs a total of 118 grams. So again, there's our water. Now I'm going to take my thermometer. So I have my thermometer in there. All right, and my thermometer is going to read that the temperature is 25 degrees Celsius. So our water is 25 degrees Celsius. All right, that's good to know. So again, I have my calorimeter all set up. I know my calorimeter weighs 118 grams. Okay, so, or my water weighs 118 grams because I deducted the calorimeter. All right, so now we got to do this quick. So I'm going to take my metal here. Again, we want to do it quick so that we don't lose that much energy. I'm going to take this metal. I'm going to take the lid off, and I'm going to hurry up, and I'm going to place it in here. All right, so let me get my yellow out again. So I'm going to put my metal in here. So my metal that was 93.5 degrees Celsius, I'm going to take it. I'm going to dump it in my calorimeter. All right, so now we're going to let it sit. We have our thermometer. We're going to keep letting it until our thermometer stops changing and our thermometer stabilizes. So we're going to wait about 10, 15 minutes, depending on how long it takes. All right, so all of a sudden my thermometer stops moving and I look and my thermometer is reading 32 degrees Celsius. So now my water started off at 25 degrees Celsius. Now my water is at 32 degrees Celsius, meaning this metal released that much energy into the water to heat it up. Because remember, it always goes from high to low. So the metal was 93.5 degrees Celsius, so that energy is going into the water. So now we know the initial and the final temperature. So now both the water and the metal are at 32 degrees Celsius. So they both have the exact same temperature because they're both in the same system now. So now we can go through and we can set up some calculations. So we know a lot about the water. So we're going to start by doing, let's find the Q of the water. So again, because we know so much about the water, that's our first step. We're going to start finding out information about our water. So we know QW. Well, we know our water mass. So remember our equation's up here. So we know the Q of the water, so we know our water's mass. Well, we know our specific heat of water, 4.184. That, again, is on that chart that you have. So there's a list of 6 of them. Go there, liquid water, 4.184. We also can find out how much water, or how much the temperature changed of water. Okay, because we know the initial temperature was 25. We know the final temperature was 32. So we can take our final minus our initial. So we can take 32.0 degrees Celsius we can subtract that from 25 degrees Celsius. And we can see how much the water changed. So we know that the water changed by 7.0 degrees Celsius. Okay, so we know that it changed by 7 degrees Celsius. So now we can calculate this out. So when we calculate that out, we know we do grams, so 118 times 4.184 times 7. We look at our units. So let's just look at our units. So grams would cancel out here. Degrees Celsius would cancel out there, leaving us with joules. So our QW is going to be 3,455 joules. But sig figs, because this one only has right here 2 sig figs, our answer can only have 2, so it would be Q of water is going to equal 3,500 joules. So that's how much energy the water is absorbing. So remember, the water was colder and it absorbed heat. So we know that this is a positive number. So we know Q is a positive number because it absorbed energy, which means, since it absorbed energy from our metal, we know that the Q of the metal is going to be negative. But again, we don't care much about the water, but this helps us find out, well, if QW is 3,500, then that means that the Q of the metal must be negative 3,500 joules because the metal gave the energy to the water. So we know that the energy transferred can't be lost or gained because we're in a closed system. So now we can use this information to figure out, well, let's figure out what we know about the metal. Well, we now know the Q of the metal is negative 3,500 joules. Well, we can find the mass of the metal. Okay, so we can go and find the mass of the metal. Oh, well, we needed to weigh the mass of the metal, so we just weigh the mass of the metal. So we know that, let's say, put on the scale, and it says, all right, it's 125 grams. So we know the mass of the metal. We just weigh it on a scale. We know delta T, because we know that it started at 93.5 degrees Celsius. That was our initial. And we know after we put it in the water, it was 32 degrees Celsius. So now we can figure out the delta T, so we can take our 32.0, because that's our final, minus our initial, 93.5. All right, so we know delta T is going to be negative, because it's losing energy, negative 61.5 degrees Celsius. All right, so we have our delta T. So we're going to just get rid of that. So our delta T, which means, all right, we can find our C. So we're going to plug in our equation. Negative 3,500 joules equals 125 grams times M, we don't know that, and then delta T, negative 61.5 degrees Celsius. All right, so our C, I'm sorry, this was supposed to be C, is going to be, when we calculate this out, 0.455 joules per degree Celsius in grams. All right, so we go and look at our specific heat chart. If you look at your specific heat chart, you should see, so we should see that, we can go back to this. Let's see which one has close to our negative 0.455, and look, it's iron. So we can say that our metal that we're talking about is iron. So we know our metal is iron that we are dealing with. And then sig figs here, we would just want to change this to 0.6 or 0.46 because of our 2 sig figs there. All right, and that